Hello, grade 12. Welcome back to the channel. In today's lesson, we're going to be looking at vertical projectile motion and we are tackling graphical questions. So without any further ado, let's get right down to the lesson. So we are given question 4. It says the following velocity time graph is obtained for an object in free fall. Neglect any air resistance. Then 4.1 says explain what is meant by the term free fall. So let's run quickly to that. We have free fall is the motion with which the only force acting on an object is the force of gravity. So that's how you define it for 2 marks. Then 4.2 says use the above graph to describe fully the motion of the object. Now we can see that we are given a velocity versus time graph, and if we have to revise our graphs, we know that if we are given an increasing function for a velocity versus time graph, this only means that we took down as positive, right? So we know an upward as positive graph looks like this, whereby we have a decreasing function. So this is for up as positive, remember, and that one is for down as positive. So now, because we can see this is an increasing function for velocity versus time graph, we know that they took down as positive, right? So now let's check what happened here. Having to describe this motion, we can see that probably here we have a scenario whereby a person is standing on top of a building, and then what do? They throw a ball upward. So how do we know that they're throwing a ball upward? Because we can see that the velocity is decreasing, and the only case whereby we have a velocity decreasing is when an object is going upward, right? So remember, when an object is going upward, it loses its kinetic energy, and hence it also loses its velocity. So if you look at the formula half mv squared, we know that a decrease in kinetic energy equals a decrease in velocity. So as the object is going upward, it loses its kinetic energy, and therefore its velocity decreases up until it reaches the maximum height, where its velocity is equals to 0. We can see that because it is indicated there by the x-intercept, we can see that our velocity for the x-intercept is equals to 0. Now we know that the x-axis on a velocity versus time graph indicates the velocity at the maximum height. So the velocity that you get on the x-intercept is the velocity at the maximum height. So now when the ball reaches the maximum height, what happens? It now starts to go downward, and then it passes the starting point here, and then it goes downward to hit the ground. So that's the scenario that we have here, that is represented by that velocity versus time graph. Now let's put that in point form and explain. We say number one, the object is thrown upwards from the top of a building, then it reaches the maximum height and moves downwards below the starting point and hit the ground. Right. Then 4.3 says calculate the initial velocity of the object. As you can see with this question, there is no data that we can highlight here. There is no data that we can read from the statement. This is where you need to take the skill of extracting your data out of the graph, right? So now you having to come to understand the graph, you will know that the y-intercept here always indicates the initial velocity of the object. So that's what we are looking for. We are actually looking for the value on the y-intercept, right? So that's the initial velocity. We don't have it. So for in case the question asks what is indicated by the y-intercept of the velocity versus time graph, you now know the y-intercept always indicates the initial velocity of the object. Then at this point here, what is indicated by the x-intercept? What is indicated by the x-intercept is the time it takes to reach the maximum height, right? So the time taken to reach the maximum height is 0.25 seconds. But what is the velocity at that maximum height? We know that the velocity at the maximum height is 0. So we know if something is an x-intercept, it has a y coordinate of 0. So 0 meters per second. Then now we have VI changing t, VF, and what can we put as our A? Now, seeing that our graph has downward as positive, we can just as well run with that. So if we take downward as positive, our acceleration will be positive 9.8 meters per second square, right? Now we have all that information. That is enough for us to calculate the VI, having to choose the first formula, which is VF is equals to VI plus A change in T. Then we say, what is our VF? Our VF is equals to 0. Remember, we are taking it from the moment it is projected up until it reaches to the maximum height. Then do we have VI? We don't have it. We are looking for it. Then our acceleration positive 9.8 and our change in time is equal to 0.25. That is the time it takes to reach the maximum height. Then we have 0 is equals to VI. Multiplying those, we have 2.45. And then if we transpose it to the other side, now we have negative 2.45 meters per second. But then we know the negative is telling us about the direction of motion. So now we have to say 2.45 meters per second upwards in this case. Remember, we took down as positive, so anything that comes out as a negative, it indicates that it is going upward, right? Now that's how we have it for 4.3. Let's look at 4.4. Now 4.4 says calculate the final velocity of the object. So now that we have the value here, which is VI is equals to negative 2.45 meters per second, we can now take the whole journey. Remember, the final velocity of the object is here, the moment when it hits the ground. So now we don't have that VF. That's what we are looking for. But this time around, we are taking for the whole journey. We are not taking it from the moment it is projected to the maximum height. We are now taking the whole journey. That means from the moment it is projected all the way up until it hits the ground, right? So now what is the total time taken for the whole journey? We say change in t is equals to 4 seconds. Then our acceleration still 9.8 meters per second positive. Remember, we said this one, once we choose our acceleration as positive, we have to continue throughout with it. Once we choose the direction like that, then we continue throughout with that direction. Then again, we can see that we'll be using the same formula as in 4.3. So we go VF is equals to VI plus A change in T. Then we don't have VF, that's what we are looking for. But remember, we calculated VI in the previous question, negative 2.45, and then plus our acceleration is 9.8, and change in time this time is 4 seconds. Remember, it's for the whole journey. Then VF is equal to, you punch that in your calculator, you have 36.75 meters per second, right? And then where is it going? It is going downwards. Remember, after the maximum height, the direction changes, and then the ball is now moving downward, right? Now we have 4.5. It says draw a position time sketch graph for the entire motion of the object. Take the starting position as the 0 position. Indicate all relevant times on the graph. Now, okay, for this one, they said take the starting position as the 0 position. So what I'm gonna do right now is, let me first take the ground as the 0 position and show you how the graph would look like if the ground was the 0 position, and now and then show you what is the difference when they say we take the starting position as the 0 position. So okay, for that one we're gonna go. So remember we have taken downward as positive, so that's how it looks like. So right now, if they had not told us that we are taking the starting position as 0 position, and they told us take the ground as 0 position, this is how we'd have it. So we'd say at that particular height, remember we don't know the height at which it was thrown, but then we know that after it is thrown, it goes all the way up. That means there's an increase in height, and then it goes back, and then after here it reaches the maximum height, right? Then from the maximum height, it starts to decrease in height, then it passes the point, the starting point, and then goes all the way down, right, up until the ground. Remember, we are saying the ground is the reference point or the 0 position. So this is how we would have our graph, right? If they had said, take the ground as reference point, right? And then this would be the time. What is the time taken to reach the maximum height? Is 0.25. So 0.25. And the time for the whole journey is 4 seconds. Now, this is not the graph that we are supposed to draw, right? Remember, they said that we must take the starting position as the reference. So basically what will happen here is that you will just shift this graph, right? Exactly as it is, you just shift it upwards, right? So that the starting point is on the 0 line. So there you have it. So remember now, when you shift it, even this line, even this point here will now shift upward, right? So this point will now shift upward. Then you have your 4 seconds there. That is the total time of the journey. And then you have your 0.25 there to indicate the time it takes to reach the maximum height. And then there you go. That's your time in seconds. And then here, this is your position in meters. So you can see that nothing changes here. It's just a matter of you having to shift the graph upwards so that the starting starting point becomes your 0 reference, right? So the graph you were supposed to draw is this one. Awesome. Now let's check question 3. It says a ball of mass 0.2 kg is thrown vertically downwards from the top of a high building. The ball bounces from the floor. The velocity versus time graph below shows the motion of the ball with the downwards motion taken as positive. So we've been told that down is taken as positive. Ignore the effect of air friction. Now 3.1 says write down the magnitude of the velocity with which the ball bounces from the floor, right? So now we can see, having to understand this, what happened here. So if we are to draw a trajectory of what happened, let's say this is a building and this ball was thrown at a velocity of 2, right? So it is thrown at a velocity, or thrown downwards, right, at a velocity of 2. So here is the person and then throws the ball downwards at a velocity of 2 meters per second. Then it goes down, hits the ground at a velocity of 9.6 meters per second. But because this is an inelastic collision, the ground won't, the ball, I mean, or the object won't bounce off at the same velocity that it hit the ground. Now it bounces off with a velocity that is lower than what it hit the ground with. So now bouncing off, it bounces off with a velocity of 8 meters per second, which is what we are observing here. You can even see this, the slant on the graph to indicate that there is some contact time with the ground there. So the graph is not going straight like that. That is to indicate that the collision is inelastic, right? Then we say write down the magnitude of the velocity with which the ball bounces from the floor. So we've already spoken about that. That's 8, right? So this is the time when it bounces off, right? So your velocity for 3.1, we say it's 8 meters per second, right? Now 3.2 says write down the magnitude and direction of the acceleration of the ball at time t. Now we can see that at time t, that's where it is in the maximum height, right? So that's the maximum height. Remember, at the x-axis here, the x-intercept indicates the time it reaches the maximum height. Then they ask us what is the direction of the acceleration of the ball at time t. So we know the acceleration is always 9.8, right? And then that's 9.8 meters per second square, and the direction of that is always downwards, right? Whether the object is moving up or down, that direction is always downwards. Remember, gravity is always acting downwards, so it's always going to be 9.8 meters per second downwards. Then 3.3 says, is the collision of the ball with the floor elastic or inelastic? Explain the answer with reference to the graph. So we've already spoken about that. We said the collision is inelastic. Why? Because we can see that there is a slant on the graph, right? We can see that the ball does not does not bounce off at the same height that it hit the ground. So we say inelastic, the ball. So we say the ball bounces off at a lower or at a lower velocity than the one it hit the ground with. It hit the ground with. So inelastic, the ball bounces off at a lower velocity or at a velocity that is lower than the one it hit the ground with. So we say that's an inelastic. Remember, inelastic collision, that's where we have a loss of kinetic energy. So because of that loss of kinetic energy, even the velocity that it bounces off with will be lower than the one it hit the ground with. Then 3.4, it says calculate the height from where the ball was thrown. Then having to calculate that, let's first have our data. So we are given the initial is 2 meters per second. So we wanted the height in which, at which the ball was thrown. So remember, from this height, it was thrown downwards. So we are looking for this height here. We are looking for the delta y from that position it was thrown to the moment it hits the ground. Then vi is 2 meters per second. Then we know that it hits the ground at the velocity of 9.6 meters per second. And then our A, because we take downward as positive, it's positive 9.8 meters per second square. And then what was the time taken? Do we have the time? We don't, and we are not given there. So let's check. We're looking for the height, delta y, right? So having all that VI, VF, A, and delta y, what formula can we use? Let's just use which one? Let's use VF squared is equals to VI squared plus 2A change in Y. So this one would be best for that. Then our VF is 9.6 and then square that. Then our VI is 2. Remember, they're all positive because they're going downward. Then 2, and then our A is 9.8, and we are looking for delta Y. Then if you punch that in your calculator, you have 92.16, and then 2 square gives us 4, so we can just transpose it this side, it's minus 4. Then 2 times 9.8, that gives us 19.6 delta Y. Then let's find the solution to this one. We have 88.16 is equals to 19.6 delta Y. Then we can just divide both sides by 19.6, 19.6. Then our delta Y in this case becomes 4.50 meters, right? So that's our solution. That means the ball was thrown at a height of 4.50 meters. Awesome. Then 3.4.2 says now calculate the magnitude of the displacement of the ball from the moment it was thrown until the time t, right? So now we wanted the displacement. Remember, when we are looking at the displacement, we are now looking at displacement is the same as us having our distance finally minus the distance initially, right? So here we are looking at the change in distance, right? A change in distance. Then magnitude of the displacement of the ball from the moment it was thrown until the time t. So now we can take here, we can come here and observe. Let's extract the data all the way to get to time t. So if we take it from the moment the ball bounces off the ground, we can say our velocity initial is equals to negative 8 meters per second. And then at this point t, remember t indicates the time it takes to reach the maximum height. Then at the maximum height, we know the Vf is equal to what? To 0 meters per second. Then what is our acceleration? Remember, we don't change it. We took downward as positive. So our acceleration should forever be positive 9.8 meters per second square. Then having to look for our delta y to get to the maximum height. Let's now check. Remember this maximum height, because this is inelastic collision. We know that the ball cannot bounce back to the height of 4.50 meters. Now it will bounce off to a lower height, right? Because it has lost energy. So now, having all the data, we can still use the same formula we used on the previous question. Then 2 a delta y. Then what is our Vf? Is 0. And then what's our Vi? We have negative 8. Remember, it's now going upward. Then 2, 9.8, and delta y, right? Then here we have 0. So, okay, let's just calculate. For this one, we have 64, positive 64. When we transpose it this side, it's negative 64. Then 2 times 9.8, we have 19.6 delta y. Then let's divide both sides by 19.6, 19.6. So we expect our delta y to be negative because now, remember, we are now going against our choice of direction of motion. We took downward as positive and now the object is going upward. So our delta y should be negative. So we have negative 3.27 meter. But then if we write it as height, our height is 3.27 meters. So it bounces to a height of 3.27 meters. Now to check the displacement, remember the displacement is just a difference in those heights, right? In this case, a difference in the height. So our delta y will now be 4.50 minus 3.27. And that will give us 1.23 meters, right? So that's our displacement. It's a change in height. Now for 3.5, it says draw a position time graph for the complete motion of the ball from when it was thrown until the maximum height was reached after the first bounce. Right, after the bounce. Use the floor as the reference point or the zero position. Then clearly indicate the following on the graph. So now we are using the floor as the reference. And remember, we took downward as positive. So that means for position versus time graph, when downward is taken as positive, your graph has to start below the x-axis. So here we indicate this is negative 4.50. And then also remember we have a height of negative 3.27, right? So now this was thrown from a height of 4.50 meters, then it's thrown downward. So what happens to our height? It decreases, right? So when something is thrown downward, we know the height decreases up until it reaches the floor or the ground. Then, but remember, this is not an elastic collision, so we have to show that contact time with the ground here to show that there is a loss of energy. Then it bounces off. Now it bounces off to a maximum height of 3.27, right? So that's how we indicate, bounces off to that. Then now we say this is time in seconds, and that side you label position in meters, right? So what is it that they wanted us to indicate? Let's check again. And they say clearly indicate the height from where the ball was thrown. We indicated that. And now indicate the time t. Remember, time t is the time it takes to reach the maximum height after the bounce. Then we indicate this is t there, right? So having it like that, you now have all the story there. It was thrown at the height of 4.50. It went down to hit the floor, and then there was some contact time there because this is an inelastic collision. Then it bounced off, and then when bouncing off, now it only was able to reach a maximum height of 3.27 meters then at time t. So that's how you have your position versus time graph. Okay, so we are given question 3. It says a ball is dropped from a height of 2 meters and bounces a few times after landing on a cement floor. Ignore air friction. The position time graph below, not drawn to scale, represents the motion of the ball. And the first thing that we can observe from this position time graph is that they took upward as positive. How do we know that they took upward as positive? Remember, we said if your position versus time graph is drawn above the x-axis, it indicates that your upward is positive. And if it's drawn below the x-axis, it indicates that down is positive, right? So 3.1 says define the term free fall. Now we say free fall is the motion with which the only force acting on an object is the force of gravity. So that's how you have it for 2 marks. Then 3.2 says use the graph and determine the time that the ball is in contact with the floor before the first bounce. So now let's understand what happened here. We can see that at a height of 2 meters above the ground, the ball was dropped, right? And then when it is dropped, it goes all the way down and hits the floor, right? But because this is an inelastic collision, it is in contact with the ground for a while before it bounces off to a new maximum height, which is lower than the one it was dropped from. So now we know in a position versus time graph, these gaps here, they indicate the contact time with the floor or the ground. That's what we are looking for here, the time the ball is in contact with the floor. So to answer that one, we have 0.67 minus 0.64, which gives us 0.03 seconds, right? Now 3.2.2 says the time it takes the ball to reach its maximum height after the first bounce. So where is the first bounce? The first bounce is happening at time 0.67 seconds, right? Then we want the time it takes to reach the maximum height there. So that means we want to check it here. So the time here we are looking for, it's actually the time in between here, right? But then if we can look at this graph, we can see that this graph is parabolic in nature, meaning that we can use our knowledge of math to get the time there, right? So what is the time there? How do we get the time? So we can just go 1.90 minus 0.67 divided by 2. That will give us 0.61 seconds, right? So the time that we have here is 0.615 seconds. Now 3.2.3 says calculate or determine the speed at which the ball leaves the floor at the first bounce. So now we want the speed at time 0.67 seconds. But now if we have to collect our date, we can see that when the ball bounces here, bounces off from the floor, it reaches the maximum height of 1.85. So we can just write that as our data. So we say the height reached is 1.85 meters, right? Then what is it that we have? We also know that at the maximum height, our velocity is 0 meters per second, right? Remember, that's where the ball stops momentarily. Then we have our A. Remember, we said upward has been taken as positive, so that's going to be negative 9.8 meters per second square, right? And then we don't have what? We don't have VI, which is what we are looking for, the speed at which the ball leaves the floor at the first bounce. Now, having all that, that means the formula we can use now, we can use VF squared is equals to VI squared plus 2A delta Y, right? Then what do we have for our VF? It's 0 because it reaches the maximum height. Then we don't have VI, that's what we are looking for. Then 2, our A now, let's substitute negative 9.8 because we took upward as positive as they did with drawing the graph. Then our height is gonna be 1.85, right? So we have 0 VI squared, and then having to punch that in your calculator, it gives you negative 36.26, right? Then we have VI squared is equals to, so now remember we have transposed the negative, now it's positive. Then square both sides, our VI is now 6.02, right? So that's 6.02 meters per second, right? Now 3.2.4 says determine the time t indicated on the graph. Determine the time t indicated on the graph. So now we want to collect data for that one. The time t that we are talking about is here, right? So we are looking at this motion here after the second bounce, right? So after the second bounce, what information do we have? So if we say, okay, let's now take it from here, this point, up until the maximum height. So the maximum height it reaches after the second bounce, it's 1.2 meters, right? and the velocity at that height, we know at the maximum height, the velocity is 0 meters per second. Do we have VI? We don't have VI, right? And then what is the acceleration? Remember, we run with that acceleration, negative 9.8 meters per second square, right? But then they're looking for time t. Do we have time t? We don't have time t, right? So with this one, we can see with the marks, that's 6 marks, and then we can also tell by our unknowns. Here we have 2 unknowns. So that means we are solving something that will require us to get 2 unknowns, right? So we can see that the problem here is we are looking for delta t, but to begin with, we don't even have the initial velocity. So the first thing we would do here is to get the initial velocity, then we can now get the delta t, right? Or the time t indicated there. Now, okay, let's go. So having all that information, we can see that we can use the same formula as we did in 3.2.3, Vf squared Vi squared plus 2a delta y. So remember with this one, I'm still looking for Vi. So Vf, that's 0 at the maximum height. Then we have Vi squared, then 2. Our a still negative 9.8. But our delta y this time is 1.2. So we have 0 is equals to Vi squared. And then punch that in your calculator, we have negative 23.52. Now if we transpose, we have Vi squared is equals to positive 23.52. Then square both side. We now have Vi is equals to 4.85 meters per second, right? So we have 4.85 meters per second square. Then let's check here. So we already have Vi, but then if we are looking for time t here. So the velocity at this point, we are saying it's 4.85 meters per second, right? Then it goes all the way up, it reaches the maximum height, whereby our velocity is now 0. But then if we can check, again, we have a parabolic graph here. So we know if this object leaves at the velocity of 4.85 meters and it returns to the very same position here, that means the velocity there is also 4.85 meters per second. But this time it will be what? Negative, since now it's going downward and our motion we chose upward as positive. So now having to collect our data, we say our Vi is 4.85 meters per second. So now we are checking the whole journey for the green graph there. And then Vf is negative 4.85 meters per second. Our acceleration is negative 9.8 meters per second square, right? And remember, we are looking for delta t, right? We are looking for delta t, so the time in between that green graph. Now, okay, having to use this formula, Vf is equals to Vi plus a change in t. We can now use that formula to get our change in t. But our Vf, remember, it's negative 4.85, and then Vi is 4.85. Then we have our acceleration, negative 9.8, and then delta t. Now, if we transpose it to that other side, we have negative 4.85 plus or minus 4.85. That gives us negative 9.7, right? If we transpose that one to the other side. Then here we are left with negative 9.8 delta t. At this point, we can divide both sides by negative 9.8, negative 9.8. Our delta t now becomes 0.99 seconds. But remember, here we are looking for t as a value, right? We are not looking for the time it travels on the second bounce. We are looking for t as a value. What is t? So we cannot say it is 0.99 here, because you can see we have 1.97. So the 0.99 is just the time in between 1.97 and t. So in order to get our t here, that means we have to do what? We have to say 1.97 plus this 0.99, right? So that's how we're going to get the value for t. So let's do that. So we have t now is 1.97 plus 0.99, and t is equals to 2.96 seconds. And that's how you could have tackled that one. Awesome.